All right, so do we have any questions on what we just covered there with position vectors? All right, let's have a look then at figuring things out about which way these vectors point and how we deal with that. Okay. There's a basketball standard. Of course, the weight of the basket pulls down, but notice that the support for it doesn't go straight up and down. It goes at an angle, okay? Now, when you're designing things like that, you focus on two things typically. Okay. So what we have here is the weight. And as you probably notice there, the weight goes down. That's going to get transmitted through that pole in two forms that we analyze. One we call axial. That goes down the main axis of the pole. That can either be tension, which pulls, or compression, which pushes. There is also a component of that weight that is perpendicular to the pole. We call that shear. Shear is a sliding kind of action. So if you're going to design that pole, you're going to design it for axial load, tension or compression, and you're going to design it for shear. Okay? And there's a lot of different ways to kind of express this. There are rather different actions in how a material will react to those things. Okay? Pushing and pulling stretches atomic bonds is what it does, or compresses them. Shear slides one plane across the other. So at the atomic level, materials act rather differently in those two modes. The other aspect of this, though, is if you're going to design something, you can't possibly rate a material for every possible angle the force might act at. You know, that's just so much information, it's too much. So what we do is we break the angled forces down into two components, one axial and one in a shear mode. We can then rate the material on its axial strength and its shear strength, okay? So this allows us an easier method of analysis, okay? So what we're doing there, we're using a bit of trigonometry, and we're going to break the weight up into an axial component and a shear component. And that's typically how you design things. We'll get into this more when we take strength of materials. But for now, let's just kind of remember some of these terms and the idea, okay? And you could probably see there's a right triangle there. If you know that angle, you could do this pretty quickly with sine and cosine to get those two components, all right? So we're good with that concept number one there, okay? Now in 2D, that's a fairly straightforward thing to do. And I've got a second example here where we have a railroad car and we have a mule pulling the railroad car, and the mule is stubborn and is not pulling down the tracks. The mule is pulling off at an angle. Okay, and let's say the mule pulls with 200 newtons, and if I know that's a 24-degree angle, I could take 200 newtons times cosine of 24, and that would get me 183 newtons of what I would call useful force pulling the cart down the track. You know, okay, with that same idea as I was just looking at, a little different application. All right. Now, in 3 space, though, that can be a little harder to do. In 2 dimensions, quite often we can get those angles pretty quickly. But in 3 dimensions, it gets a little bit more challenging. So we need a mathematical tool to do this with. And the tool we'll use is called a dot product. Okay. All right, a dot product can be used to find the angle between 2 vectors, which would help us solve this problem here. Okay, and this is a vector operation. I don't know if you've had Math 254, or if you're in it, you might be starting to touch on this already. I don't know. Now, in a math class, you'll use this in a very general sense. In an engineering class, we have a use for this, and we will focus on our uses for it. Okay, so a little bit more focused than a math class would be about this. Okay, this is a dot product. It's A dot B is how you say that. A and B are vectors. What you get when you dot A with B is the magnitude of A times the magnitude of B times the cosine of the angle in between. Okay? So when you dot 2 vectors, you get this term AB cosine theta. Notice the dot product of two vectors is a scalar. Okay? The dot product of two vectors is not a vector, it's a scalar. Also notice that the cosine of 0 is 1, the cosine of 90 is 0. So if you dot two like unit vectors together, they have magnitudes of 1. If you dot I, j, and k, what you get is 1 for the answer, because they make a 0-degree angle with each other. If you dot two unlike unit vectors together, they make a 90-degree angle. So anytime you dot two unlike unit vectors together, you get 0, because they're 90 degrees apart, and the cosine of 90 is 0. All right? So if we're going to dot two vectors together, we would use the distributive property and dot every component of A with every component of B. So we'll get AX BX, I dot I, AX BY, I dot J, AX BZ, I dot K. Then we'll go AY BX, J dot I, AY BY, J dot J, AY BZ, J dot K. Okay. AZBX, K dot I, AZBY, K dot J, and AZBZ, K dot K. So what I'm doing, I'm taking AXI dotted with BXI right here. And I'm just separating the AX and the BX and the I and the I. Here I'm taking AXI dot BYJ, I'm separating it into AXBY times I dot J, et cetera, okay? And the good news on this, the bad news, it's a big, long, 9-piece calculation here. The good news, though, is 6 of them cancel out, because anytime I dot unlike unit vectors together, they go to 0. So what ends up happening is that. So when I dot two vectors together, even though the beginning piece there is fairly complex, the end piece is pretty simple. If I dot A dot B, all I got to do is take AX BX, add it to AY BY, add that to AZ BZ. That's all I got to do a dot product. That's how you do a dot. Okay. So down at the bottom of the page, I got an example. If I got 3 minus 4, 2, and I want to dot it with 2, 5 minus 6, I just take the like components. I take the x's, 3 and 2, and I multiply them together and get 6. Yeah, I screwed up, didn't I? Should be an X right there, thanks. Do you have any typo on your page that corresponds? I don't think you do, but do you? Sometimes. It looks like I did that. Is that all clean on your copy? That's good. Thanks. Okay. So you take the like components, multiply them together, take the J's, multiply them together, and then take the K's. So 2 and negative 6, multiply those together. Add everything up, and you get negative 26. Okay. All right. So that is a mathematical operation. As engineers, we're a little bit more focused on how are we going to use this, okay? And we can use it to do two things, typically in engineering. One, we can use it to find the angle between two three-space vectors. And the other thing we can use it to do is to find the axial component of a force on a support, similar to what we were looking at here. If I want to know if I know the weight of this basket here, and I want to know how much of it goes down the axis of that support pole, I can use a dot product to help me figure that out. Okay. So let's have a look how to do that. Here's a little picture of what I'm talking about there. I've got a force at an angle, and it's pulling, or pushing, I should say, on that support there. What would the magnitude of that be? All right. And the way I could notate that, there's not a nice clean way to do it. So the way I do it, I say FBC parallel to AB, meaning the component of FBC that is parallel to AB. That's my little notation there. Okay. So let's have a look at that. So I want the projection of FBC onto line AB. Okay. Now what that is FBC times whatever that angle between them is, theta. The issue I've got here in 3 space, I don't know what theta is. I got to kind of work through that. Okay. So what FBC cosine theta is FBC. I'm going to just say times 1 times cosine theta, and I'll explain that here in a minute. Okay. Now, I've got a nice little mathematical tool here that's A dot B is AB cosine theta. Notice that looks like it might fit into this little way I've written this up, doesn't it? Okay. So if I want to find the projection of FBC onto that line, the way I'm going to do it is I'm going to take FBC, that's the A part of my formula. I'm going to dot it with this line BA, that's the B part of my formula, but I want that to have a magnitude of 1. So I don't want to use the full vector AB or BA. I want to use the unit vector. Okay? If I do that, the B part of my term there will just be 1. Okay? So I've got FBC for my A part of the formula. For B, if I use a unit vector there, that'll just be 1. What that is UBA. Okay? And then when I do that dot product, I get the cosine of the angle in between. Okay? So to figure this thing out, to find the projection of BC onto AB, I'm going to take FBC dotted with U, unit vector BA. That's what I'm going to do. Okay. Doing all right with that? Okay. That's the process there. Okay. Now, if I want to find that angle, again, I can go back to that definition of the dot product. A dot B is AB cosine theta. If I want to find theta or cosine theta, what I do, to find cosine theta, I take A dot B over AB, which is the same as UA dot UB. So if I want to find cosine theta there, I just take unit vector BC and dot it with unit vector BA, and that'll get me the cosine of the angle in between. Okay. So that's how I can find out that kind of stuff that I might want to know as an engineer. Okay. So to find FBC parallel to AB, the projection of BC onto AB, I take FBC dotted with UBA. To find the angle theta, I can find the cosine of the angle theta by taking UBC dotted with UBA. That's how I will use that in the engineering analysis I want to do. All right, got any? Might be better shown by example. I don't know. That's kind of a lot to say there, but that's how we do what we want to do. You got any questions on that? Okay. All right. All right, another example there on 210, I think. I want you to find the coordinates of A, B, and C. Start with that. We always, want to do that when we're doing our 3-space stuff. So I got 0, 0, 0 for A because that's the origin, 0, 0, 7 for C, 4 minus 3, 5 for B. All right. And then we start following the steps there. So we good with the coordinates? Questions? Okay. All right. So 0, 0, 0, 0, 0, 7, 4, negative 3, 5. Okay. All right, then off we go. You got RC, subtract off RB, get R from B to C. Okay, that will be a position vector that goes from B to C. So what we're doing here is what we just did earlier. We're finding we're going to find a force vector from B to C. So I'm just outlining the steps there. So find RBC first. Negative 432. Is that how we get from B to C? All right. The next thing to do after you got that is to find the magnitude of BC. So how long of a line is that? Usually 3 places. You know, these are all even. Oh, on the unit vector, you want 3. Positive 3 is 0 minus negative 3. That's a nice 3 again. So I got 5.39, 5.385, something like that for the length. Is that right? Divide through by that to get the unit. So divide through by that, you get that unit vector, and then scale it up to get a force vector. That's the first step, is to get a force vector. Okay, so just scale that up by the amount of the force. So 300 newtons. We'll scale it up by that. So negative, I got 4 places there, negative 228, 222.8, 167.1, and 111.4. Okay. And then when we carry on with that, we want to next, so we good with that, with the force vector? So we'll do this, a few times. You want to get comfortable with this. This is a process that we use a lot. Okay. Okay, now we want to find a unit vector from B to A. So it's very similar to what we just did, with the exception that we don't scale it up by anything. We just want a unit vector this time. This is a unit position vector. It's pointing the direction from B to A. So that's the next thing to do. Okay, so just take A minus B and you'll get BA. I think that's minus 4, 3, negative 5. And find its magnitude and divide through by it. You'll get the unit vector. Okay, let's see. We're starting to run a bit short of time. We're not going to get all the way through this one, so, but we can go ahead and do that. A couple other things. Now, when we do our recitation, when we go over homework, I post the slides for that. I don't know if you noticed that in Moodle, but I put those up there if you want to look at them. Okay, they're there. Oh, let's see. I've got a meeting to go to on Friday, so I'm not going to be here. Can't get anybody to fill in, so we'll take Friday off. Okay, so I got to go to a meeting. And I'll get you a couple more of these to do for Thursday. We'll cover these tomorrow. For Thursday, how about doing 151 and 153? So we're going to have 3 of them due on Thursday, right? So 151 and 153. Was the other one 143 that was due, just so I get a complete list? Is that right? 143? Okay, thank you. And so that'll be due Thursday. We'll cover them tomorrow. And that is the 10th. Okay. So those 3 are due on Thursday. No class Friday. Okay. We'll finish this thing up tomorrow, I think. So, any questions on anything? Doing all right? Okay. Call good?